Next, we will kick off a new part of the textbook, which is on management science. And in this chapter, chapter 5, we're going to be transitioning from a lot of the type of math we've been doing so far into something entirely different. And the goal of these first few videos is to set up an introduction to graph theory and get some of the um, terminology and stuff down that is used throughout the next 4 chapters, which are kind of the next big block of what we're covering. So in the first 4 chapters, we're focused on math of social choice, like elections, weighted voting systems, and power apportionment. Basically, how do we do things fairly, and what issues do we encounter in a society with fairness? To which, unfortunately, in each chapter, there was always a little bit of a problem. There's not necessarily a clear-cut answer. So, anyways, from here on out, we're going to be doing stuff very different, and we'll be finishing up with some finance right before the final. But chapter 5 is what I wanted to set up in this video and do an introduction to. And chapter 5 is titled The Mathematics of Getting Around. And what we're going to be focusing on are what are called street routing problems. Basically, it's a new type of problem where we're trying to determine how something should be routed across the street. For example, think about how UPS drivers deliver their packages, or security guards patrol neighborhoods, or stuff like that. Those are the type of problems we're going to be focusing on in this chapter. So let me go ahead and get the slides up, and like usual, I want to set up with an example. What is the problem? What does a problem look like, similar to those we'll be solving? Then we'll develop the math that actually goes into solving the problem. So basically, I'll go ahead and read this. It says a private security company has been hired to patrol the following neighborhood, and they will begin at the corner of Hill Street and Sunset Cliffs Boulevard. So this is a section of neighborhood very close to PLNU. Sunset Cliffs area. And basically, imagine that we are a security guard and we are supposed to make sure there's no crime going on in the neighborhood. The question is, what is an optimal path to cover every street in the neighborhood? Optimal meaning best. In path, we'll define what that means shortly. But obviously, we kind of get the idea of what that means without having to look at the mathematical definition of those things in graph theory. And then a separate question is, if we were to change the starting point, would that give us a better could we find a better route from a different location? So before we get into the math of solving it, we could kind of imagine basically we're starting here and our goal is to patrol the entire neighborhood. And notice that the condition is that we want to hit every street in the neighborhood. So like imagine that we just do one big circle like this. That's not exactly a solution to this problem because there's a lot of streets in the middle. And to really properly patrol it, we want to go down every single street and make sure no crime is happening. But we could imagine before looking in the math that goes into this, we could think about a potential solution. Like let's say we head down Sunset Cliffs Boulevard and go all the way to the end. We could then make a turn on Ladera Street and then make another turn onto this unnamed street, which I don't know off the top of my head, and continue down this way, and so on. And we kind of traipse back and forth across each of these longer streets as we go. And then we can move down Corinth Drive, kind of like that, and then come down Hill Street. And notice that we've covered a very big portion of this neighborhood. But some of the issues as well, there's certain streets that I left off in that potential. Like, for example, every street like Marseille or Monaco or Brindisi or whatever. Like we could think about, well, I could continue and weave my way back and forth through all the streets that I miss as I continue. But notice that in doing this, as I'm weaving my way back through those streets, I'm traveling over sections of street which I've already patrolled. Like in my initial route, I kind of went like this and went down here. So I've already hit really all of this Corinth or whatever that street is, and I've hit this street as well. But if I was to weave my way through these other streets, notice that I'm actually kind of redoing some of the travel which I already did, and there's a little bit of wasted travel in this problem, and that's a term which we call deadheading. So the first definition is deadheading is wasted travel in a street routing problem. Basically traveling over the same stretch of road more than needed. And so more than needed is something like, well, that this is a question that we're going to be seeking to answer as we examine the math in this chapter is, well, is that deadheading that I did, basically traveling along this section of street more than once, was that necessary? Or was there a way that I could travel along every one of these streets without wasted travel? And it turns out there's actually a relatively simple answer to this question in 5.3. But before we get into all the ways of answering these questions, we're gonna talk about a lot of terminology and graph theory, because we're gonna not just be using this in this chapter, but every chapter up until chapter 8. And an optimal path avoids deadheading. So basically, if we could have zero deadheading, that's what we'd want. Because if I'm patrolling this neighborhood in a efficient way, hopefully I don't have to go down any street twice, right? Ideally, I could just hit every single street exactly once and return back to the start. But what we'll see is that that's usually not possible. And so instead of trying to get zero deadheading, due to the impossibility of that typically, we're going to try to minimize it if at all possible, which we actually refer to as optimally Eulerizing the street routing problem.